we have 4 presentations today, so they're going to go a little quicker. I will actually be giving the first presentation, presenting the one of the juvenile synthesis that we contracted out through Thomas Gass and Associates. So let me share my screen.
Oh, for sure.
Okay, does everyone see the proper screen? Okay, so this is basically a long-term evaluation of the data collected at the Willow Creek screw trap. And this is a picture of our crew just getting the thing ready to go out for the season. So a little backstory on this, the outmigrant traps in the Willow Creek were established in the late 1980s. They've been operated annually since 1989. And we use these to assess population, outmigration timing, and timing and duration of various salmonid species, mostly Chinook, but we do get quite a few coho and steelhead through there as well. There's been several models developed to estimate passage. We have a flow-based, a mark recapture, and then what we call the HDAT, which represents the HUPA daily average temperature. And this one actually relates the timing with the accumulated daily average water temperatures. And then in 2016, the Yurok tribe published a request for assistance to further develop some of these statistical analyses and models to synthesize this long-term data set. And then in 2017, we selected Thomas Gass and Associates, and they produced the bulk of this report for us. So here's in case you don't know the Trinity River, this is a map of Trinity with the Pear Tree Trap and the Willow Creek Trap. So we're pretty far down on the system, and this kind of represents basically what's going out to the Klamath. You know, there is a few more tributaries and a little bit of spawning below Willow Creek screw trap, but the bulk of the spawning is above. So the objectives of this synthesis report was to evaluate the influence of water temperature on the outmigration timing of Trinity River Chinook salmon. Second was to evaluate flow-based and mark recapture estimates as the predictors of RT50 and RT80. And RT50 and 80 are basically when 50% of the run has passed and then 80% of the run has passed. The third objective is to quantify the predictive ability of the HDAT model proposed by Tim Hayden and Tony Keacock, who both worked for the Yurok tribe back in the, I guess, mid-2000s, 2010 or so. And the last objective was to evaluate the historical differences between Chinook salmon abundance and population pre and post rod. So we're going to move on to our first objective, which is to evaluate the influence of water temperature on the outmigration timing. This is a raster hydrograph of the Trinity River at Hoopa. And you can see that basically by mid-July, you know, post-rod, the black line there represents the rod. So above that is post-rod, and then below that is pre-rod. So you can see that it's pretty variable. There's about a 10 to 12 week window where this outmigration, you know, where we hit those RT50s or 80s. And we'll talk a little bit more about the actual timing a little bit later. So this is, you know, outmigration. One of the main triggers for outmigration is temperature. This is temperature at Helena and the Pear Tree screw trap. So you can see that basically once the water gets warm, those fish tend to move out. You know, it's again, it's, you know, about a 12-week period where most of this encompasses, and it's pretty highly variable from year to year, but it generally takes, you know, generally within that 12 to, you know, 12-week range. This is going downstream at Hoopa, and we see here that it gets, you know, the water temps are of course quite a bit warmer, and that the out migration really you really see it happen once those colors turn red. So those fish know once that water gets to that, you know, mid 70-degree mark that they need to be gone. And so on this raster hydrograph, the red here is actually almost is 80 degrees. So, you know, that's
Wow.
way warm for salmon. So we looked at a bioenergetics equation to simulate the growth and consumption of juveniles, because you know, temperature is probably the most important variable controlling growth. So knowing, you know, when fish grow and when they don't is really important. So we use the Wisconsin bioenergetics model in R, and that the Wisconsin bioenergetics model is like the model to use when it comes to growth and consumption in the fisheries world. So it's definitely the best one to pick here. And we noticed from running this model is that consumption generally declined sharply in late April during, or the model concluded that we see consumption decline sharply in late April during the spring rod flow releases. And this model links link consumption with discharge and density. So we have, it's positively correlated with a higher discharge in February through April, but it's negatively correlated with the number of reds and discharge in May. So basically when there's extra competition because of the number of reds, we use that as a surrogate for basically out migrants, because we have a lot of good data for that. So basically when we have lots of reds, we expect lots of baby fish and higher competition, which will lead to probably lower growth because of it. So this is a raster graph of showing kind of that consumption fall off that we see with the rod flows. So in late April there, you basically what we should be seeing is we should be seeing blue, yellow to red as temperatures increase. But instead what we see is kind of this blue, yellow, sometimes red, depending on if it's a dry or water year. And then this blue, which is the drop in temperature associated with the rod flows. So basically we're limiting growth during the rod flows. Okay, let's move on to our next objective, which was evaluating the flow-based and mark recapture population estimates as predictors for the RT 50 and 80. So on the left there, that figure shows the mark recapture population estimates for the Willow Creek trap, and then on the right is the flow-based estimates. So you'll notice that right in the middle there, above in the post-rod section, you see a lot more red than in the flow-based. And this seems to be the theme, is that the flow-based seems to underestimate, well, one of them is either overestimating or one is underestimating, or one of them is correct and one of them isn't. And that's something that we need to determine. But another thing you'll notice is that the flow-based, since we're not dependent on mark recaptured fish, it allows us to extend basically our season. There's a lot of times early or late in the season where we don't have fish to mark recapture. We get very poor results because of the higher low temperatures. So this allows us to have, basically fill in gaps that we might not be able to do with the mark recapture. So this figure shows the mark recapture estimates plotted against the flow-based estimates, and the y equals x means that they're basically even. So everything along that line there would be basically an even estimate. And you'll see that there's a lot more red dots below the line there. So that means that we're consistently having higher mark recapture population estimates. And so we'll talk a little bit about why that is. So like I said, we have this consistently higher estimates for the mark recapture. Both of these methods rely on a set of assumptions. Mark recapture is generally a more accurate method. It relies on what I think is a few less assumptions compared to the flow-based. So the biggest assumption is that the mark recapture method assumes that all marked fish released upstream of the trap passed by within the following week, and it doesn't account for fish that are preyed upon, die, or don't migrate. And if for those fish that are removed from the system, though the mark recapture method will overestimate the abundance. So we can actually do a few things to counteract that, some of which we have done, but that's probably the biggest. And especially later in the season, we do see a lot of our fish, our mortality rates go up just because the temperatures are so high. So that's definitely a valid assumption. And then the flow-based assumes that trap efficiency is relative to the stream flow, and that the juveniles are evenly distributed throughout the stream channel. And we know that's probably not the case. So the way the flow-based one works is we know how much volume of water goes through the screw trap over a set time, and we can actually extrapolate that out to the entire river. So that's a pretty big assumption that occurs with the flow-based. We have tested several of these assumptions. I do not believe any of them have been published yet. And unfortunately, Paul Petros was one of the ones that was responsible for a lot of these. So when he passed it, I'm not sure of the exact status of some of these. So some of the ways that we don't know which way is better. They have their advantages and disadvantages. Like I said, my preference is for the mark recapture. That seems to be more accepted, but it does have limitations. And so some of the other things we can get around this is by maybe doing some acoustic tracking, or any other way to track fish three-dimensionally as they pass by the trap will help us address some of these assumptions. So our third objective was to quantify the predictive ability of the HDAT model. So basically this model is just a linear regression used to estimate out-migration timing based on water temperatures. So when they first came up with this model, they only used 2005 through 2013, and it seemed to work great for that. But when you applied it to the longer time series, it didn't seem to hold up. And it also was a better fit for the flow-based estimates than the mark recapture. So those figures on there show the R-squared values. Basically, when you expand it out to 91 to 2016, we lose. It becomes noticeably less accurate. We go from an R-squared of 0.77 to 0.485, and that's kind of a point of you question its usefulness. So they explored several other new models. We use PDAT, which is the pear tree version of HDAT, some temperature thresholds, and then accumulated temperature unit thresholds. And some of these models fit the flow base better, or they almost all fit the flow base estimates better than the mark recapture. And you can see the one with the arrow down at the bottom is the pear tree accumulated thermal unit thresholds, which are the best, seem to fit the data the best over the longer time series. So this is what basically what the model results look like through that time period. And you can see again, as we see that kind of same trend where the RT80 and 50, once that turns red, those fish need to be gone. And that kind of yellow to red period is when we see, the bulk of the fish moving, completing their migration. And that occurs again in early to mid-July. And again, it's only about a 12-week period where this all occurs. So we also explored some multiple regression models using temperature, red counts, and median emergence date. One of these models stood out using these 3 variables. And it's the equation on the right there, which the 3 variables are the day of year accumulated temperature starting on day of year 60 when it reaches 500 at pear tree. And then the emergence date, and then the red counts. And so that had an R-squared of almost 0.8, but unfortunately it only uses 12 years of record, which using 3 variables on 12 years of record is not generally a good idea. So we should definitely re-examine this once we get some more data points. So our last objective was to evaluate the historical differences between Chinook salmon outmigrant abundance pre and post rod. The differences between pre and post rod were tested using non-parametric methods because this data is not normal in the least bit. Mark recapture and flow base were highly significantly different pre and post rod, and post rod juveniles were more abundant. Other general linear models were also highly significant. And then we explored the relationship between red counts and outmigrants, and we saw no significant relationships in low R-squared values. So that figure there on the right, you can see the p-values there. So generally it was pretty highly significant for both. And this is a graph to show the trends and pre and post rod, with the one on the left being the mark recapture, and then the one on the right being the flow base. So you can see there is some overlap, but generally the averages are higher. But they are higher post rod compared to pre rod, and actually our abundance is trending up post rod compared to pre rod, but this only goes up to 2016, and we know 2017, 18, and 19 were all pretty low abundance spawning years. So that might be a reason why. It's hard to make these assumptions for something with such a limited, with only such limited points in a highly variable population. So conclusions from this. We said the juvenile Chinook abundance significantly increased post-rod, and we've seen that with other modeling exercises like the S3. Warmer water temperatures during the initial rod flows could increase the potential for growth and could encourage earlier outmigration, and that might be important with the disease issues in the Klamath. And we're seeing a lot of our fish get coming down with various diseases as they hit the Klamath. So getting them out earlier before it has a chance to establish itself might be really good for the future. We see that potential consumption rate is variable from February through April, and then a lower consistent level during the rod flows. The HDAT performed worse with a longer time series, and the best explanatory model to describe Outmigration timing includes pear-tree accumulated thermal units and pear-tree temperature thresholds. We said the multivariate models for outmigration should be explored, but there's just not enough time series data for practical use. And then we said that the flow-based estimates are consistently lower than mark recapture estimates. And that's all I've got. So I have got a couple minutes for questions if anyone has them. Let me bring up my participants list here quick so I can see. Yeah, go ahead, Bill.
Yeah, thanks, Chris. The presentation. I was curious about the consumption that you showed, and there was that heat map of consumption, and showed that in April consumption drops off, and I guess there was one that stood out, 2012, where it looked like consumption actually stayed high during that April period. And so my question is, what is your thought on why consumption drops off during that high release period?
It's 100% temperature. In that consumption graph, let me bring it back up. I have to reshare my screen, but so in that consumption table, it's consumption and growth are highly linked to temperature. So we have colder temperatures, they won't grow as fast. And this
Can you show slide 9?
Yeah,
I think that's one that
goes. Yeah, so that why in 2012 that it doesn't seem to drop off as much.
2008
or 2008, yeah. So that says it is a dry year. So that probably has something to do with it. Just we didn't get as much flows that year. I'm not sure. I'd have to go look at the flows that year. And it's we would still expect though, if you're that warm earlier, you'd expect that trend to continue, and it's more of the negative trend as we progress further in the year, where you would expect a positive trend. I think that's kind of the takeaway.
And these are the temperature that was used for this model is, where was that measured?
Yeah, so this would be the results from the Wisconsin's biogenics model, and temperature and ration are the two things that influence growth. So if ration's staying the same and temperature increases, your growth isn't going to be as high. So,
right, but this is consumption. So this is
oh yeah, this is consumption, sorry.
So that's how much these juveniles are
consuming
to based on like the size, I guess, right? So you're saying the fish is this size, so it must have consumed this much based on the temperature profile.
Yeah, sorry.
No, that's fine. I just I'm just trying to work it through my head. And where was the temperature, the input for this? The temperature was measured where?
I think it was at Pear Tree.
Okay.
If I remember right.
Yeah, that kind of makes sense. I think there's some good information in here, and I think the program should dig a little deeper into these years that stand out, where we see results like that, like 2012, 2008. It's worth looking a little deeper and saying, okay, well, why do we see these results that these 2 years stand out? Was it that temperature was higher, and was temperature higher because of dam releases, or was it environmental? Was it like was it just a really warm year temperature, air temperature wise, and therefore water temperature was higher? Or is it because flow was lower, temperature was higher, or is it because dam releases, I know that the temperature of the water released from Lewiston is fairly, it's fairly stable. It's not a huge change from year to year, but I do know that residence time in Lewiston Reservoir can impact the water temperature as it's being released. So I feel like that there's some information here that could help us in water management. So I'm trying to tie this back, how does this help us change management? Well, understanding how these levers and dials change the physical setting, which then impacts the biology. I think that's kind of like the logical next step after these, these long-term analyses, is to do some true synthesis reports where we're actually taking, merging, and this kind of does that, where you're taking data, temperature data and flow data and fish size, and you're kind of looking at, what the expected, looking at the impacts of, the physical setting on the biology.
Yeah, and we are working, one of the projects that was funded a couple of years ago now, but was using the S3 model to kind of to change some of those dials, and using it to figure out kind of these anomalies that seem to happen, and figuring out how we can, the S3 model has so many different inputs that you can use, that we can start really dialing in, what we need to do management wise to hopefully get more fish out.
Yeah, that 2012 year stands out to me because that was our highest juvenile abundance year. And I always wonder, well, why was that year so much better? Well, you'd expect if there was strong density dependence that, well, this of course is model.
Yeah, this is all modeled, so this was,
it's not, it's not the actual. So anyway, just this, I was like, wow, why did consumption stay high in those years? And so I think that's worth digging a little deeper.
Okay. Yeah.
Thanks.
Do we have any other questions? Bill's up next, so he's just taking up his time. So
it's my strategy.
I don't see any other hands, so you can go ahead, and you should be able to share your screen, Bill, as well. I believe and Bill is going to be talking us about, this is the Fish and Wildlife Services effort for juvenile Chinook production. So it's similar but different. So whenever you are ready, Bill, go right ahead.
All right. See my screen?
Yep.
Do you see my cursor?
Yes.
Okay, good. So I have a pointer. All right. Well, thanks, Chris, for the introduction. Whoa, something just broke. Thanks for the introduction. That was a good setup for what I'm going to talk. So I'm going to take a little bit more of a dive into our abundance estimates and talk about more, and these are the marker capture estimates. So I'm not going to touch on the flow-based stuff, because that analysis that Tom Gast and Associates did kind of dug into that question there. Let's see. Okay, so these analyses that I'm going to present are all going to be based on naturally spawned age 0 juvenile Chinook salmon. So our our population estimation routine, which was developed for the Trinity River Restoration Program by Carl Schwartz and Simon Bonner, takes the weekly catch values and marker capture estimates and creates a season-wide weekly stratified abundance estimates. And so for Willow Creek, we've got data from 1989 to 2018. And there were some years that were flagged as bad. And some of these years, like the year 2000, sampling didn't start until May. So we missed, a good portion of the early part of the year. So we decided to throw that out. 1993, there was a lot of problems with the trap operations, and there was just a whole lot of missed trapping days. And as well, 2006 was similar. It was an extremely high water year, made sampling extremely difficult. Very few fish were captured until the hatchery release occurred. And then, so we felt like 2006 wasn't a good representation of the population. So there's some years in the time series that have been removed. So for the pear tree site, which is at Helena, which is right the North Fork of Trinity River, just above the confluence with the main stem, 2003 to 2018. There are a couple years. 2006 also was a bad sampling year there, and 2005. There were some again some sampling issues there, and so those 2 years aren't included in pear tree. So I mentioned, these are, we're going to look at the marker capture weekly stratified abundance estimates. I'm only going to present the yearly totals, so I'm not going to do the week by week estimates. So again, it's only age 0. We've kind of backed out the age 1+ Chinook salmon, which can be abundant in some years, and especially early in the season at Pear Tree, because Pear Tree tends to get in the water earlier than Willow Creek. At Pear Tree, sometimes we see a fair number of 1+ Chinook in, say, January, February. And so those have been backed out. So we're really looking at, the emigration, which is, the downstream migration of age 0 Chinook salmon. And I'll present some data on fork length towards the end. So measures of abundance. How can we convey abundance? Like how strong of a year class was it? So population estimates, what we generate from our trapping sites. Basically we come up with number of individual fish. So 2,345,912, something like that. Now that's a very specific and precise number. It may overstate the precision of these estimates, but nonetheless. So how many fish do we estimate? But we know that, and especially from like what Chris showed, that potentially when there's a whole lot of fish out there, there might be some density dependent effects. And so if we have a high number of fish, we might be getting smaller fish because there's less food to go around. So we estimate biomass, which basically taking the weight of the fish. So it says fish size. It is really the weight in grams times the population estimate. So for a week, we have we measure a whole bunch of fish. We get a distribution of fish weight and just multiply that by the population estimate. So we have estimates of a weekly biomass, and those again are summed up for the season to come up with kind of yearly estimates of numbers of fish, and then also like how much biomass is produced. It's useful also to, we know that adult runs are highly variable. And we know generally if there's more spawners, we'll get more juveniles. So, just looking at numbers of fish, it's difficult to kind of tease out the effects of management and the effects of restoration and whatnot. So we've corrected our population estimates and biomass estimates by number of spawners. So just numbers of individuals per spawner and biomass per spawner. And then I'll dive a little bit into stock recruit models, which are useful for assessing density dependent effects between spawner abundance and juvenile abundance. So abundance and biomass, what do we see? We started at pear tree, and if we just look at the long-term time series from 2003 to 2018, we'll note that 05 and 06 are absent from this time series, that there is no long-term trend in the time series. But we do see some, some banner years. Look, here's 2008, here's 2012, which intrigues me. Chris, I was like, what's up with that consumption? Because look at that, we've got these couple of years here that kind of stand out. So there's pieces of the puzzle that are kind of coming together here. So if we now then look at biomass of individuals, so we incorporate size. Now, if you go back and forth between this one, you'll see you get a couple of these, lots of individuals in these years. When we look at biomass, well, now those peaks aren't as high. We get some pretty good error bars around these. And again, no significant trend through time, but my point is that this is abundance, numbers of individuals is kind of has more variance. So you get these high peaks and then these lower ones, whereas biomass is a little less variable over time. The difference between year to year is less, and so that's also intriguing. That it hints at perhaps there might be a capacity to the system. So again, but no trend over the long-term time series. Now, when we look at juveniles per spawner, so the abundance corrected for numbers of spawners, we do see the significant positive trend. So what that's saying is that, it looks like that it's trending in the direction that we're getting more juveniles per spawner. It's not necessarily a good thing. I'll get to that when I talk about stock recruit. And then, so that juveniles per spawner correct, biomass per spawner, sorry. We see the stats tell us that there's a weak positive trend here. So again, that's some tentative positive results. This might actually it kind of follows the juveniles per spawner, where you're getting kind of more biomass per spawner in the recent years. But again, I don't think that's necessarily a positive thing, and I'll touch on that in a few slides here. So switching downstream, looking at Willow Creek, looking at the entire time series from 1989 through 2018, we do see a significant positive trend in abundance. So these are just numbers of juveniles. But we do know that right here in the middle of this time series, we started implementing the record of decision flows from Lewiston. They were supposed to happen in 2004. We did release some water in 2004, according to the ROD, but full implementation happened in 2005. And it does look like there's so I'll break that out into pre and post record of decision flows. It does look like there was a marked increase in abundance You know, our estimates do tell us that. And this 2004 really, you know, kind of stands out as being kind of low. It probably should be lumped with the pre-rod, but you know, it's included in this post-rod thing. But we don't, although this does look like it's trending down, it's not a significant trend. So there's no, you know, these are not significant trend lines. So looking at, you know, post-rod mean, the long-term mean is about 2.5 times what the pre-rod mean was as far as juvenile abundance. So that's to me, that's a real take-home positive effect. Who would think putting more water in the fish tank can hold more fish? So that's my fish tank analogy there. So so again, we see some, you know, positive influences of the record decision flow, but we don't see any trend in abundance or biomass like a pear tree, which is all post-rod, and not all. There's a couple years in the beginning which are pre-rod, but we just lumped them into that. So so in stock recruit, this is assuming that there's a non-linear function between the numbers of recruits, in this case, the numbers of juveniles leading the system. And this happens to be a results slide that got put out of order. So let's skip past this. Oh gosh, darn it, my order of the slides got all messed up. Okay, so again, a pear tree, juveniles per spawner. I have some duplicate slides here. I'm going to skip through. I apologize. Okay, here we go. Willow Creek biomass per spawner. So I was at the Willow Creek pre and post rod. The biomass per spawner. Now, there's not as significant of a change between pre and post, but we do see what appears to be a weekly positive trend, although it you know, stats say it's non-significant post rod. All right, back to stock recruit models. Here we go. Apologize for that. So stock recruit models, again, can compare the recruits, the juveniles, to the stock, which is the spawning population size. Stock recruit models by design are non-linear, and they were designed to manage fish populations for maximum yield. So it's a thought that as spawner populations get really high, you're getting less and less return of or less and less recruits or yield because of density dependent competition for food and space and whatnot. So the theory was, well, hey, let's fish the population down a little bit and maximize the numbers of recruits that we get per spawning stock. So that's was the theory. It doesn't necessarily work in practice, but it allows us to investigate whether there is a potential density dependent effect. So here's the pear tree spawn recruit curve. The dashed line happens to be the a linear relationship between juvenile and spawner abundance. The curved line is a Ricker model, which is nonlinear. In this case, the Ricker model fits the data better than the density independent or the linear model, and so there's some evidence that there's a density dependent effect. And what you can see here is that it looks like that the peak production of juveniles happens around a spawner size of, you know, around 10,000 spawners, at least in this time series that we have. Then we look at Willow Creek spawner recruit. We have a longer time series that we can look at pre record of decision flows and post-record of decision flows. And so the dashed line here is pre-record of decision with the open circles, and then post is the solid line with the filled in circles. And in both these cases, in both pre and post rod, the Ricker model fits better than the non-linear or the linear model. So there, at both the Pear Tree and the Willow Creek site, there's evidence that there's some density dependent effects going on. Now, when we look at, so Willow Creek again captures the entire basin upstream. So there's a number of spawning populations that are not captured by the Pear Tree site. So you notice that the spawner abundance here for Willow Creek to maximize juveniles. Now it's difficult to say with the post rod because we have this high one out here, but at least in the pre-rod section, it's maybe around 30,000 spawners to maximize juvenile production, even though our highest pre-rod juveniles per spawner happen at a fairly low abundance size. Now these models, the way they're designed, are designed to go through the zero, the 0, point here. And so anyway, if you look at the pre-rod, it looks like the highest abundance, estimates of juveniles happen at less than 20,000 spawners, even though the curve itself kind of maximizes out at around 30,000. So again, in a system that pre-rod was quite habitat limited, we would expect density dependent effects to kick in sooner than in a system where habitat is not limited. So, I mentioned before when we looked at the Pear Tree juveniles per spawner, that had a positive trend through time, and that there's a tendency to say that's that we got to focus on that and say, yeah, it's positive through time, so that's a good thing. Well, if we look at this figure shows just a relationship between spawner abundance and then juveniles per spawner, and so if we were increasing juveniles per spawner through time, what that means is, if we were going to maximize juveniles per spawner, we want to keep our spawner abundance down quite low, right? And that's not what we want to do in the program. We want to have more spawners. So by focusing on juveniles per spawner as a metric is not necessarily I think what the program would want to do. Now, there are some potential useful uses of juveniles per spawner. And again, that same figure for Willow Creek, I just put in a non-linear curve here. It just seemed to visually fit the data better. Again, so if we were going to maximize juveniles per spawner, we want to keep our spawning population low. Again, I don't think that is a goal of the program to maximize juveniles per spawner. I think we want to maximize the number of adult salmon that return to the river. So that's kind of comes to the end of the abundance section, but there are, there's a ton of data from the trapping thing. There's a lot going on in this figure. So I'm going to leave it up for a little while and explain what's going on here. So these are a week of the year, which starts in about March at the beginning here. This is just for Willow Creek. And so for week, in any particular week, let's say week 15, I took the entire period of record, pre-rod and post-rod, and grouped all the fork lengths together for pre-rod and post-rod. So in week 15, this dark gray is all of the fish prior to 2005. for week 15 lumped together. And again, the lighter gray is the post rod. And what we found is that in almost all cases, early in the season, the post rod fork length was higher than the pre-rod until we got to about where the record of decision flows occur, when they start to occur in April-ish, and then post-rod fork length decreases, is lower than pre-rod fork length. And so what happened with the record of decision flows? We started releasing more water downriver. And what Chris showed is that, temperatures are depressed, and the bioenergetics model showed that the consumption decreased. And what we're seeing here is, if you look at an unregulated river system and salmon growth, you would see fork length increasing through time. But what we see is this flattening off of fork length. And so that is, again, piece of the puzzle. We think that temperature is depressing growth. And furthermore, with the record of decision flows, that we are even further depressing growth. So, if you look at, this is a different graph. These are violin plots. So it kind of, these are kind of density plots of fork length, pre-rod versus post-rod. Fortunately, with the fork lengths, we can't really tease out all of the hatchery fish. For our population estimates, we have a routine where we can estimate, numbers of hatchery fish and kind of back those out of our population estimates. When we go to fork length, we don't have that ability. So for those who aren't colorblind, this aqua color here are the non-ad-clipped fish. The red bars are the ad-clipped fish. And then these two here are pre-rod and these two are post-rod. But what we see is that both ad-clipped and non-ad-clipped fish are smaller or shorter fork length than pre-rod. So it looked like pre-rod we're getting a little more growth, post-rod we're getting less growth. So preliminary conclusions. So it did look like there was a significant increase in pre versus post in abundance, juveniles per spawner, and biomass per spawner when we're looking at the Willow Creek, because that's the time series where we've got good amount of time either side of the record of decision flows. At the pear tree and the Willow Creek site, we don't see a significant trend in abundance and biomass post rod. So again, there's a lot of that has to do with the decrease in adult spawners coming back, especially in the more recent years, potentially masking any potential habitat, positive effects of habitat on juveniles. We did see a significant positive trend in juveniles per spawner and biomass per spawner. Again, I think that that's due to the fact of low spawner population size and density dependent effects, allowing more access to food and habitat for the juveniles that are there. We did see a significant shift in the Ricker curve, the spawn recruit curve, and I think that's a positive take-home message. But again, the fork length, size of juvenile Chinook salmon, age 0 Chinook salmon is significantly smaller post 2004. So metrics. So what what do we use as a program to track success of juveniles? I think it's useful to not just focus on one, but to use, you know, a series of things. So Juveniles Per Spawner and Biomass Per Spawner, I think, could be useful in assessing kind of capacity of the system, especially at low spawner population size. So that although, you know, I don't think we want to use it as a metric of what we're shooting for, it allows us to assess, you know, some capacity of the system. So I do think that we should be tracking juveniles per spawner, but we don't want to maximize that as a metric of the program. You know, perhaps looking at the stock recruit curves and the model parameters is probably a better metric, because it's incorporating you know, some nonlinear density dependent effects, and allows us to kind of look at that, track that spawning population size that maximizes production of the juveniles. And I think the goal of the program is to shift that to the right, so that as we get more and more spawners, we're getting more and more juveniles. And I think I repeated this Willow Creek slide. So, you know, what we really like to see is more of these points out here where we're getting, you know, a lot of spawners, and then also a lot of juveniles being produced. With that, that concludes my presentation, and I will take. Do we have time for questions? It sounds like
we can probably do like one question if anyone has one.
Okay.
I don't
Yes,
see
I got a question, but I don't. Where's the raise hand function? I don't see it.
It's under reactions.
Okay, you want me to raise my hand?
Oh, you can go ahead, Ken.
Yeah, Bill, can you go back to the? I have two questions actually. The plot of the boxed time series of box and whisker plots of lengths. That guy. I think I might already know the answer to this, but I'll ask anyway. So post rod lengths, you know, we attribute that, you know, the decrease there, the leveling off that you're showing, and the lower, smaller sizes compared to pre-rod, attributing that to temperature suppression from rod releases. But what explains the leveling off there?
Yeah,
pre-rod period.
It's funny because when I was talking about this, I'm like, oh, I forgot about what's happening here. There's a bump up here with the arrival of hatchery fish in that happens right around this time period. So the leveling off actually starts taking place a little earlier if we were to truly exclude all the hatchery fish. But what, you know, we had hatchery fish are released basically the same first week in June throughout the entire time period. So we see that it happens right around, where is it? It's I lose track of my weeks. It's right around here. So this bump up is really the arrival of hatchery fish, and then as that wave of hatchery fish comes down in a fairly short period of time, and then kind of peters out. So some of this is due to that. So that especially in this time period, a lot of this kind of bump there is due to larger hatchery fish showing up, fish that are larger.
So maybe like what's really going on in the system absent hatchery fish might be as if like weeks, let's just say 22 through 26, like if you just deleted those and put a straight line in between, it would maybe take out a large portion of the hatchery influence on those sizes.
Yeah, correct.
You still have increase, but it still levels off. It's just not nearly as dramatic as it looks there.
Yeah.
Okay. So then can you go to violin plots too?
Where, how can, oh, there we go.
Yeah, so I'm just curious your thoughts. What I see here is that, there's a pretty strong pattern in the no clip fish that matches the hatchery clipped fish. So it seems like a big portion of that is that upper lobe on the green ones is actually just hatchery fish, which is, of course makes sense. But that seems to imply that those larger fish are not the natural origin fish, and that for the most part, the natural origin fish are like the bottom extension of those lobes, and then those bumps down at the bottom. And it looks to me, well, first of all, I guess, does that interpretation seem right to you?
Well, so this is the entire sampling season. So I do think that that yes, it is likely that a fair number of this non-clipped fish are likely hatchery fish. But again, this is Willow Creek, and it's incorporating juveniles from the basin upstream of Willow Creek. So I think what we see here is like kind of newly emergent fry in this kind of bottom lobe. But we do know that there are natural fish coming through that, especially later in the season, will be close to 100 millimeters and perhaps larger. So I wouldn't say that all of these fish in this bulge that correspond with this clipped fish, I wouldn't say that they're all hatchery fish, but it could potentially be driving that. The point of this was to kind of lump these two classes, clip and no clip, pre and post rod, to look at and to test for differences. And in both, if we look at just this clip and this clip, I mean, post rod, the hatchery fish are smaller at Willow Creek, suggesting that and there hasn't been a decrease in the size of fish released from the hatchery. So I think there's growth that occurs between the hatchery and Willow Creek, and I just think there was more growth happening pre-rod than post-rod.
Okay, so I assume like the volumes or widths or sizes of the green versus red is not proportional to abundance, right?
Correct. These are just fork length measurements. So, the width of this here is just like how many fish were measured at that fork length.
So the reason I ask if you think that a lot of that upper lobe is hatchery fish, and if the lower lobe is not entirely, but largely natural origin fish, what I see here is like that lower portion has both dropped down in mean fork length, and it's gotten wider since the rod implementation, which my interpretation is that there are more smaller natural origin fish than pre-rod. Does that square with your understanding?
Yeah, I would caveat that to say that there were more fish measured post-rod. So we did kind of increase our sample size post-rod. So I think some of that is due to the fact that we were just measuring more fish.
Okay.
So I think, we do, based on the abundance estimates, it does appear that there are more natural origin juveniles out there than pre-rod. So teasing out sampling effects versus abundance effects is tricky in this case. But because I had the other supporting evidence of the population estimates, I would say yes, but I don't know that that's the reason why this one is wider than it is here.
Okay.
So.
Okay. Thank you.
Yeah, no problem. Looks like Kyle has his hand up. Do we have time for another?
I don't want to take up any more of Ken's time here. So
Okay,
maybe if we have some time at the end, Kyle, you can.
yeah, I'll be on for the duration. So if there's time at the end, I'd be happy to take questions.
Okay. All right. So our next presenter is going to be Ken, who's going to be presenting his cohort reconstruction synthesis report.
Okay, let's see here. Okay, do you see?
It's
my
the correct one. Yeah.
Format? Okay. Okay. Yeah. Thanks, Chris. So for those of you who don't know me, my name is Ken Linke. I'm an environmental scientist with California Department of Fish and Wildlife, and I work full-time for the restoration program. I'm going to talk to you today about a cohort reconstruction model for the Trinity River that's focused on naturally produced or natural origin fall Chinook salmon. Here, get this going. Okay, so here's a list of what I'm going to cover over the next like 20 minutes or so. I'm going to go over what a cohort reconstruction is, because I know not all of you are super nerdy fish biologists that get into this really dry stuff. And then explain the differences between brood year production, which is the result of a cohort reconstruction, versus run year escapement, which is what we commonly understand for abundance, adult abundance. Go over why it's important, why we need to do this work for the TRRP, and what the status of the project is and what we expect to get from it. So I'll just have to say there's spoiler alert here. The model's not yet to a point that I can run it with the Trinity data. So I don't have results to share with you, but so this is more of a project update with some additional background information and some new methods that I've had to develop to get this project going. So just to set everybody's expectation going in. Okay, so we're going to go through a conceptual depiction of a couple cohorts as they age in the ocean and return to freshwater. And this is going to kind of an introduction of what a cohort reconstruction is. This first bubble that you see represents a cohort of fish that are in the ocean at age 2, immediately before their opportunity to return to freshwater as age 2 jacks. So as we walk through this slide, everything on a horizontal line with this bubble in line with it horizontally or above it is our fish that are in the ocean. And then everything below the bubble are going to be returns to fresh water. So at some point in the fall, some portion of the cohort matures, returning to fresh water to spawn. The cohort model uses a monthly time step, and this occurs on September 1st, but we can just think of it as, around fall time. We can call that a birthday. So fish remaining in the ocean turn age 3 at that point. And the age 2 jacks are returning to freshwater. So a year later, those age 3 fish that are remaining in the ocean, they do the same thing. Some stay in the ocean and become 4-year-old fish. Some return to freshwater as age 3 adults. And now you know the story. So the same thing happens for age 4 fish remaining in the ocean. And we also assume that all fish mature at age 5. So that was just one cohort, but of course, there's always multiple cohorts co-occurring in the ocean and in freshwater. So here's another cohort in blue. That same dynamic of ocean residence, freshwater escapement, and aging occurs. And you can see this cohort, it's advanced to the right relative to the white one, just to kind of roughly signify calendar years. Of course, there's more than 2 cohorts out there at a time, as shown in part by this green one. So, how do we make sense of all this in terms of brood years and run years? Run years are just what they sound like. In a given fall or winter, the run, quote unquote, or freshwater escapement is comprised of fish of different ages from different cohorts as shown by these boxes. And so each of those boxes would be a run year or freshwater escapement estimate. Only 2 cohorts are shown here in each box. But you know by now that each run comprises fish from 4 cohorts from ages 2 through 5. Brood years or brood year production, on the other hand, it's a metric of interest in cohort reconstructions. It's actually the primary output. It's a little bit more complicated. The cohort reconstruction accounts for all the fish of a given cohort or brood year across multiple years and across space. So that's freshwater and the ocean. It also accounts for many other quantities and parameters that aren't shown here for simplicity, such as harvest, natural mortality, age-specific maturation rates, contact rates in ocean fisheries, non-landed mortalities in ocean fisheries, drop-off mortality rates in the ocean and freshwater fisheries, among other things. So the model itself is far more complicated than we can depict here, and has many other outputs besides like the primary value of interest, which would be brood year production. And all those can be useful for various other investigations. So let's look at this in a slightly different way to really make it clear for y'all. So run years, escapement, freshwater returns, whatever we want to call them. This is the common and intuitive metric that we're all very familiar with. It's basically how many fish came back. It's used in all sorts of management decisions, including relevant to us, the evaluation of restoration performance. So something to note here, which should be obvious at this point, is that each run year is comprised of multiple age classes. Brood years, of course, this is showing brood years, are also comprised of multiple age classes, but all the fish numbers are organized back to the year in which they were all hatched. So while annual monitoring, like our weir work and red counts, focuses on estimating run years, but fisheries management often relies instead on models to reorganize run year estimates into brood year production using cohort reconstructions. So as an example, all the fish produced in 2009 returned to freshwater in run years 2011 through 2014. So one additional thing to note here is that brood year abundances in the top panel are much more variable than run year escapements. So just to keep in mind, what I'm showing here is what I call a naive cohort reconstruction, because it just reorganizes age-specific abundances in a run year back to their brood year of origin. But it doesn't account for any of the harvest or mortality rates that allow us to estimate the real production of brood years. And that's the purpose of a cohort reconstruction. So that difference in variability between run year escapement and brood year production means that brood year productivity is obscured if you're only looking at the much more common metric of run year escapement. Run year escapement can be used to effectively evaluate, cannot be used to effectively evaluate early life survival or total cohort production, because it's comprised of multiple brood years that have different early life survival rates, not to mention ignoring harvest and other sources of mortality. Brood year production derived from a cohort reconstruction, on the other hand, is the appropriate metric to address these questions. So from cohort reconstructions, we get the direct metric of brood year performance. So how many adults are made per juvenile. It's the best adult metric to evaluate early life survival and production, and it allows survival and production to be compared to causative factors. So for example, possibly disease in the lower Klamath, drought conditions relating to freshwater temperatures and flow, or ocean conditions, and it allows us to start teasing out how much those different factors affect how many adults come back for the juveniles that we're producing. So why is this stuff important for TRRP? Now, the IAP is like a little dated given our recent objectives and targets exercise, but the natural production and harvest remain a central focus of the restoration efforts. Brood year production's the most appropriate data for a smolt to adult metric. So again, that's number of adults per juvenile, which is kind of the other side of the coin from what Bill just showed you, which is juveniles per spawner. So combined with other data that we were already collecting, namely run year escapement and juvenile production, that allows us to close the loop on a life cycle model in the future. It's also the best way to quantify contributions to dependent fisheries from our actions, which is another fundamental objective of the program. So where does this project stand? After many trials and tribulations trying to pull this thing together, we do finally have a model, but it's in a beta phase of development right now. I can detail the road that got us here. To this point, if people are interested, we'll have plenty of time after I'm done here. But suffices to say that for now, we're looking at a model that's nearly identical to the cohort reconstruction submodel that's used in the Klamath Ocean Harvest Model. That's the KOHM acronym on the screen there. And it's been implemented in the R statistical programming language. The KOHM has been used to manage the combined Klamath Trinity stock for decades. So using this model means that estimates that we generate and any subsequent analyses that come from those will be consistent with broader management of this stock. And I think that provides a pretty big benefit personally, because then anything we do can be compared directly to what's happening on the broader scale in the Klamath Trinity. And something I'll touch on later is that the way we're approaching it would allow for an independent Klamath specific, excluding the Trinity, cohort reconstruction. But I'm not going to get into any more detail there at this presentation. Unfortunately, I'm still in the early stages of learning the model and testing the beta version. And for reasons I can elaborate on later, the authors of the R version, they don't want the model shared until it's been fully vetted. I'm working directly with the Ocean Salmon Project and the Southwest Fishery Science Center to validate and test the model. And once that's completed, I'll be able to share it with other agencies within TRRP. And running the model at that point should be relatively trivial and quick. We already have all the data, it just has to be basically formatted and run through it. And then of course the report has to be written. But one critical problem that has to be solved that's independent of this R implementation is the separation of Klamath and Trinity natural origin fish in the lower Klamath mixed stock fisheries, specifically the Yurok tribal fishery and the recreational fishery. So that's the last thing I'm going to detail here today. And in the interest of time, I'm only going to kind of briefly describe this method that I propose to use. You know, this issue is probably familiar to many of you that have been in the program for a few years. We've talked about this in Fish Work Group and other forums extensively at times. But this method in particular should be new to you, because I think actually Bill is probably the only one that's seen it. And actually some guys at the Ocean Salmon Project, but that's not relevant here. So you can see the central assumption of the method right there on your screen, and I'll read it. So age-specific proportions of Trinity River hatchery versus Iron Gate hatchery fish harvested in a given sector are equal to the proportions of Trinity versus Klamath natural origin fish harvested in that sector. So important thing to note here is that we have to separately estimate the contribution of Trinity natural origin fish to the total natural origin harvest for each age class in each year and in each harvest sector. And in this case, a harvest sector is either the recreational fishery or the Yurok tribal fishery. So using coded wire tags, we can estimate the proportion of Trinity versus Klamath hatchery fish. And then we apply those proportions to the natural origin component of harvest. Because the way we estimate harvest now, we estimate a total harvest on natural origin fish per age, but we can't separate the stocks. So that's what this is intended to do. So we apply that proportion from the hatchery fish to the natural origin component, and boom, we have an estimate of Trinity natural origin harvested age in a given run year and harvest sector. Now, of course, there's additional assumptions, of course, and there's some sample size issues, and there are other complications, but I think this method has more benefits and fewer drawbacks compared to two other methods that I've investigated. So what are these benefits and drawbacks? As you might guess, the benefits here indicate shortcomings of the other two methods that I looked at. In contrast, the drawbacks are shared more or less with the other two methods. And this is not a complete list. So benefits include that the method only requires data collected from the harvest sector in which the estimates are derived. So doing this work for example, the lower Klamath recreational harvest only requires data from the lower Klamath recreational harvest. It doesn't depend on other data collected either in the Trinity or the Klamath Trinity Basin combined. Another benefit is that it's not possible to estimate more harvest of Trinity natural origin fish than the total estimated natural. Now that seems like, well, yeah, obviously, why would you want, how could that ever make sense? But one method that was, we investigated had that property, and we see that in other spheres too. So if people are familiar, for example, with hatchery escapement, sometimes we estimate more hatchery fish returning to the hatchery than the total number of fish, and that's just a matter of sampling error and expansion. But this method does not allow that to occur. And also this method applies equally to Klamath and Trinity stocks. So as I alluded to earlier, in the future, it paves the way for a Klamath specific cohort model if anybody ever wants to develop one. But there are some drawbacks. So for, as I mentioned, like it's sensitive to sample sizes of coded wire tag recoveries. So as you can imagine, when the method has to be applied for specific ages in a specific year in a specific harvest sector, and it relies on recovery coded wire tags. By the time you've drilled that far down into the data, the coded wire tag recoveries become pretty sparse at times. So that is an issue, but that's an issue for all the methods that have been investigated. It also relies on some assumptions about run timing of the hatchery versus natural fish within the stock, either Klamath or Trinity, as they relate to the timing of harvest. That I'm not going to elaborate on here, but I can if people have questions. And there's a like I said, this is not a complete list, but it gives you kind of a flavor. So what do we expect to get out of this work? Well, for one, we get, as I mentioned, brood year specific estimates of total production. That's kind of the holy grail, so to speak, of what we're after here. We also will get estimates of contributions to dependent fisheries by sector. And then the combination of all those would be total harvest for a given brood year, which is the metric for which we have the harvest target for fall Chinook. And so we have something similar for spring Chinook, but we're not doing that cohort reconstruction yet. So it also provides the appropriate data for smolt to adult ratios. Like I mentioned earlier, it allows us to close the loop on a full life cycle model. It will allow us to evaluate trends in adult production versus adult returns. I'll mention that already, data for the full life cycle model. And in the end, we'll have a tool that we can use to continue this work into the future. And that's all I've got for you guys today. Sorry it wasn't a little longer, but I'm happy to answer any questions that you have.
Yeah, thanks, Ken. We've got a couple minutes for questions. So if anyone has one, you can use the raise hand feature.
I can't see the screen anymore. So are you
Yeah, I'm looking now.
all right, cool.
Okay, Wade, I see your hand is up. Why don't you go ahead?
Hey, I thought I'd give Ken a question 20 feet away, but hey Ken, on these
Lean into your speaker there, Wade. I can't hear you. You're cutting out.
Oh, sorry, I always forget I have this docking station I have to open up. Can you hear me better?
Yep.
Okay, sorry about that. On these expected outcomes, I see one evaluation of trends in adult production. Do you see this tool being useful for evaluating environmental variables associated with, flows, temperature, or things of that nature to help us in some way determine if we're providing better survival opportunities or environments, or is it too far outside of the smolt life history only to really do that?
No, I think this is that's definitely a potential out. It's not going to be it's not going to be in this report, but the data will be generated, the estimates can certainly be used for that, especially when paired with the estimates of total production of juveniles. So like specifically for the Willow Creek screw trap, if we have estimates of the total number of natural origin fall Chinook emigrating in a given year, we can directly relate that to the production. And something I didn't mention is that when I'm talking about brood year production, generally that's defined as like the number of fish alive immediately before their opportunity to return as H2 fish. So basically everything, it encompasses freshwater immigration and early ocean residency. And so if we were using the Willow Creek trap, for example, that would include survival or mortality from Willow Creek screw trap to the estuary or to the ocean. And so the work that Bill provided speaks to performance of the river basically upstream of Willow Creek weir. And then, the type of analysis that you're talking about would be more or less like, okay, now we got them to Willow Creek. How well are they performing downstream of Willow Creek? And we can look at how that has changed pre and post rod.
How far back, Ken, do you think you're going to try and shoot for your first brood year that you use this?
Yeah, that's a good question. The crux actually is data from the lower Klamath harvest sectors. All of the other data goes back to 1978, so that's a really long time series. But yeah, I don't have it in front of me. There are at least a few years prior to implementation of the rod that we have good data in those sectors. It's a little sparse for the recreational fishery. And but you know, I suspect that for the most part, those sectors probably contribute a pretty small portion of the overall picture, that all the abundances that are needed for the cohort reconstruction. And so I haven't given this much thought, but there might be opportunity to fill in some of those missing years with auxiliary data if we can find it. But I'll certainly be trying to maximize the number of years pre-rod that we can look at, because that's obviously really important to better understand the effects of our, you know, management actions.
All right, thanks, Ken. We're out of time for questions for Ken, so if we have some time at the end here, we can revisit some of these presentations. But Steve, I guess if you want to go ahead and get yours ready, and Steve's going to be presenting the results from the adult synthesis report.
Yeah, hi, I'm gonna share my screen here. Hopefully it worked. I know I had trouble last time. I tried to do this. I'm getting a notice that the host has disabled attendee screen sharing.
You should be good to go now, Steve.
All right, can you guys see it?
No, we don't see anything right now. There we go.
All right. There we go. Now you're seeing full screen. Sorry about that. Okay, as Chris mentioned, this is a TRRP synthesis report in draft. It's the assessment of adult salmonid spawning in the Trinity River. The principal investigators are from the U.S. Fish and Wildlife Service, myself, Nick Salm, Ken Linke from CDFW, Kyle and Chris from the Yurok tribe, and George and Billy from the Hoopa Valley tribe. This is a pretty comprehensive report. There's a few key, I think for the purposes of this presentation, I'm just going to focus on a few key points and some kind of larger picture items. Starting with the second section in the report, adult salmon monitoring and escapement. This is the weir-based monitoring conducted by the state and Hoopa Valley tribe, where we collect data from 4 runs of salmon in the Trinity River: fall runs Chinook, spring run Chinook, coho, and steelhead. In this presentation, I'm going to focus on the 2 underlined sub-items at the bottom: natural area escapement and hatchery return composition of natural and hatchery produced fish. Here we see a time series of spawning escapement to natural spawning areas of the Trinity River from 1978 or 1980, depending on the species, to 2018. The dashed lines denote the TRRP escapement targets of natural origin fish to natural spawning areas. So escapement targets of naturally produced salmon generated by the TRRP have largely not been met since implementation of the ROD. Escapement estimates of naturally produced fall run Chinook salmon and steelhead have not met the escapement targets of 62,000 and 40,000 adults respectively since implementation of the rod, and may have not met targets pre-rod in any year since reliable escapement estimates have been available. And that's the period of record that goes back to 1978 or 1980. Unless natural origin proportions were particularly high in those pre-rod years. In contrast, the escapement target of 6,000 naturally produced spring Chinook salmon adults was met in 4 of the years since implementation, and an escapement target of 1,400 naturally produced coho salmon adults was exceeded in 7 of the years. Here we're bringing up a time series of fish returning to Trinity River hatchery from 1978 to 2018. The dashed lines here denote TRRP escapement targets of hatchery origin fish to the hatchery. Escapement targets for returns of hatchery origin fall and spring run Chinook salmon to the Trinity River hatchery have been met in six or 7 times respectively for those 2 runs since 2002. And the targets for coho salmon have been met 17 times since 1997. In contrast, the hatchery target for steelhead has only been met 3 of 27 years in which data are available. The next section of the report is the spawning grounds surveys. It has here that the Fish and Wildlife Service and Yurok Tribe have worked on this section of the report, though the other partners listed at the beginning do participate in these surveys. Mention that. And in this section, I'm going to focus on the underlying subjects, pre-spawn mortality and trends in red abundance and distribution. A little more on the spawning ground surveys and the objective and purpose. These surveys are used to assess the spatial distribution of Chinook salmon reds, particularly in relation to TRRP management actions. To quantify Chinook salmon spawning in the main stem river, to quantify pre-spawn mortality of female Chinook salmon, to quantify and describe temporal and spatial distribution of natural and hatchery origin Chinook salmon spawning, and to collect ancillary biological data such as fork lengths and jack proportions, sex and age compositions, etc. Here we see a temporal distribution of pre-spawn mortality of fresh female Chinook salmon carcasses observed from 2009 to 2017. I think what I'd like to point out here is that if you look at week to week, pre-spawn mortality rates might be highest at the beginning of the season, but that's also when fewer fish are in the river. So the highest proportions of the total run in the season that are hit by pre-spawn mortality, it's fairly uniform and occurs when most fish are in the river. And here, I think the highest pre-spawn mortality, the highest number of fish that of the run that have succumbed to pre-spawn mortality is in calendar week 47, which I believe corresponds to either late October or early November. Now, we analyze red abundance and distribution at various scales, the largest being the system scale, which would be the whole river. And then at reach scales, which are, you know, smaller segments of the river, and then at the site scale, which is even more specific. These are the distributions, the abundance at the system scale over time. I guess the driver of the relationships is the restoration reach, where most of the fish spawn. So if you look at that middle column, you can see over time that we've had an overall decrease in the salmon reds from 2002 to 2017. We've also noted a change in distribution of fish. These are graphs of the mean distance of reds from Lewiston Dam, mean distance from dam from 2000 to 2017, which has mostly affected natural origin Chinook salmon. You can see on the left graph around 2002, the mean distance from dam is, you know, around 10, 15 kilometers. And by 2017, it's more down to 40, 45 kilometers from the dam. So the change in distribution is likely explained by one or both of these two scenarios. The distribution of spawning has shifted downstream as a result of more rearing habitat downstream and fish returning to their rearing grounds to spawn. Or the second possibility is that the populations that spawn further upriver have suffered size reductions. I have a number of these kind of large picture graphs that show the time and space of numbers of reds. These are the numbers and proportions. And they both kind of show the similar thing where, you know, where most reds are constructed is up in the Lewiston Reach, and as I've said, the mean distance downstream, the mean distance from the dam has moved downstream, and you can see that here where, you know, in 2002 and a little later, you know, spawning was highly concentrated in that Lewiston Reach. But the Lewiston Reach has had fewer and fewer reds over time. And then we've seen reds, the proportion and number of reds grow in some reaches further downstream, particularly like the Douglas City Reach. And I believe this corresponds to either the Junction, Douglas City and Junction City reaches. And we've also seen a higher proportion of reds down in Willow Creek over time. And the annual reports have analyses of each individual reach for you know, a more specific description of what's going on. This is a similar graph, except at the site scale. The spatial temporal distribution of the annual proportions of natural origin Chinook salmon reds in the main stem Trinity River. Again, the proportion of reds at Lewiston has kind of dropped from 2002 to 2017. Most of these sites haven't changed much, but we've seen kind of a positive response in the proportion of reds down by like Dutch Creek area, Deep Gulch, Valdor Gulch. Some of the syntheses, syntheses and new analyses that we've conducted for this report. In this presentation, I'm going to focus on these bottom four: the causal effects of pre-spawn mortality, red superimposition, red dewatering, and the distribution of reds in channel rehabilitation areas compared to unrestored areas within the restoration reach. So Chinook salmon annual pre-spawn mortality rates in the restoration reach were compared with the pre-rod and full implementation of the rod periods. The period from 2000 to 2005 was not included in this analysis because pre-spawn mortality data was not differentiated between the restoration reach and the entire main stem Trinity. Median annual pre-spawn mortality, variance between years, and overall range were greater in the pre-rod time period. In addition, 4 years from the 1980s and one from the 1990s emerged as outliers where annual pre-spawn mortality rates were disproportionately greater. When we compared the mean and variance of annual pre-spawn mortality rates between the two time periods using the non-parametric Mann-Whitley U test and Brown-Forsyth tests, which revealed no significant difference between the pre-rod and full implementation time periods. That leads us to believe that other factors such as water temperature and run size more likely influence pre-spawn mortality. Earlier, I showed a pre-spawn mortality chart over time. This is by reach. And you can see where most fish, as expected, where most fish spawn is where the largest proportion of the whole run has suffered from pre-spawn mortality, and that's in reaches 1 and 2, with very low rates or very low proportion of the total run being affected in reach 3 and below. This is a pre-spawn mortality rates from female Chinook salmon carcasses relative to the total escapement of Chinook salmon in the Trinity River from 1988 to 2017. So a paper that most of you are familiar with, Aguilar, from 1996, hypothesized that a positive relationship between the pre-spawn mortality rate and run size existed for Trinity River Chinook salmon from 1978 to 1995, but no empirical evidence was provided. A generalized linear model was developed using escapement as the explanatory variable and pre-spawn mortality as the response variable. And our findings agreed with Aguilar that the years with the higher escapement generally also had higher rates of pre-spawn mortality. The next section is on red superimposition. Now, red superimposition occurs when a female salmon constructs a red in a location that overlaps the area of another salmon's existing red. And high levels of red superimposition can be a major source of mortality for incubating salmon embryos. Traditionally, superimposition is thought to occur when the abundance of spawning salmon is high and the amount of available spawning habitat is limited. On the Trinity River during the post-dam area, the density of spawning salmon has been highest in close proximity downstream of Lewiston Dam and location of the Trinity River hatchery. These graphs show the distance to the nearest red in reach 1 and the restoration reach below reach 1 and downstream of the restoration reach, where the blue dotted line represents a distance of 3.4 meters between reds, which is the estimated distance at which reds begin to overlap. And the red dotted line represents a distance of 1.7 meters between reds, which is the estimated distance at which egg pockets become superimposed. And you see in the restoration reach, below reach 1 and downstream, there might be superposition of reds, but the egg pockets are disturbed. But we do see some degree of egg pocket disturbance in reach 1. And here we have the relationships between red numbers and undisturbed reds and undisturbed pits in reach 1. In the restoration reach, downstream of reach 1 and downstream of the restoration reach in the Trinity River. Now there's a positive relationship between undisturbed reds and the number of reds, but we see kind of a carrying capacity limit in reach 1. A carrying capacity of around 220 is evident by this curve. And that said, that this is the carrying capacity where reds are disturbed, not where pits are disturbed yet. But if the carrying capacity of reds is around 220 of undisturbed reds, I'd expect the carrying capacity of undisturbed pits to be about 4 times that, since the red areas are about 4 times the size of the red pits. So that would put us in more like the 800 or 1,000 range, which is out of our scope of available data. So I think if this line were to continue, I'd expect it to plateau soon after this last data point in reach 1. Next, I'll talk a little about red dewatering. Red dewatering occurred on the main stem Trinity River during each of the 2013 to 2016 spawning seasons, but infrequently and severity was generally mild. The annual number of reds that experienced any degree of dewatering ranged between 0.3% and 1.1% of the total reds in the main stem. Reds that were dewatered, that occurred after the high flow reduction to 450 CFS. And then the other half of the reds that became dewatered, that occurred after the winter base reduction to 300 CFS. And though we do not have data on the interior environmental conditions of the dewatered reds, those reds with a partially exposed mound likely maintain satisfactory condition for incubating eggs, since we expect that surface water was maintained above the red pit. However, those dewatered reds found with a fully exposed mound and fully exposed pit did not have surface flow and were presumably exposed to extended elevated temperatures known to decrease egg mortality or increase egg mortality. Looking at the distribution of reds and channel rehabilitation areas compared to unrestored areas within the restoration reach. At the reach, so the proportion of reds in rehab sites within the restoration reach declined at a rate of about 1% per year from 2002 to 2017. The relationship is pretty tight and steady, but at 1% a year, quite gradual. Looking at the reach scale, the proportion of reds in rehab sites compared to unrestored areas, we saw no change in the Lewiston, Limekiln, Junction City, and North Fork reaches, and an increase at Douglas City. And looking closer at the site scale, we saw red proportions increase at 5 of the 20 sites between pre and post construction periods. And that occurred at the Sven Albertson, Indian Creek, Lawrence, Upper Junction City, and Wheel Gulch sites. Our latest addition to the report, and which is still under construction, is the recommendations section. And our co-author, like I said, this is still under construction, but we've compiled a list of 9 recommendations from our findings and kind of next steps. And they're listed here. I see that we're running out of time. So I think for the sake of time and to allow questions, I'll leave it at that. And we can get into more detail at another time.
Steve, can you just back up to that recommendation slide?
Yeah. Can I? Go back. There we go.
And I see Wade with his hand up. So why don't you go first, Wade?
Okay, yeah, thanks. Hey, Steve, nice presentation. Appreciate the time you took to put that together. Had one question. One of the first slides, there was some hypotheses proffered on why the distribution of reds was moving downstream. And I think I heard you say due to potentially better rearing conditions. And I'm wondering if there was thought or analysis that evaluated actual spawning conditions like gravel size and distribution. And the other thing is, you know, the Lewiston reach had not been augmented with gravel for a number of years, which might explain the drop of spawners in that section. And I'm just wondering, curious, anecdotally, if now that we had some gravel injection up there this past year, if we're seeing higher numbers utilize that upper Lewiston reach.
Yeah, so let me see if I can remember the first question. No, we didn't analyze the gravel composition in this report. That's kind of the next step that we hope to follow after this set of synthesis reports, to kind of combine findings from other synthesis reports. And so, but yeah, in this report, we don't do an analysis of the gravel composition spatially. And as far as the gravel augmentation this year, yeah, there seems to have been quite a response to that new gravel put in. In fact, the crews mid-season had to stop counting reds because it just got indistinguishable. You know, all that fresh gravel was easily overturned by spawning salmon. There was a high proportion of hatchery fish this year that sounds like spawned in that reach based on the number of snouts that the ad clip snouts that the crew collected. And while the other while spawning activity started dropping off in, you know, November, December in the lower reaches, like it was still pretty hot at in late November in those upper 2 reaches. So I think the 2021 data, I think there is going to be a shorter mean distance from dam because there was so much spawning in that reach 1 on that new gravel.
Yeah, I just asked because I know there's been a lot of debate about whether or not to put gravel in that reach, and you know, some of the issues of hatchery spawners spawning there. However, it is, you know, does offer a lot of spawning habitat, and the program and scientists have kind of flip-flopped back and forth on whether it's a good thing to put gravel there or not. So I don't know, that might, this year might open up that debate again. I'm not sure, but I think we've evolved to supporting it. But it, you know, a lot of those graphs were showing the lack or the decrease in spawners from that reach in more recent years. And now here we have a year with fresh gravel and they're back. So that's why I was asking about the availability of, you know, spawning gravel and some of those other reaches. Rather than having good rearing conditions, it may be more of a function of spawning gravel. A hypothesis, I guess.
No, absolutely.
That's it. Thank you.
I see a hand from Eric.
Yeah, given that the hatchery reach was not sampled through a lot of November, and how that might impact the total number of reds that have been counted. Wondering, are the reds in the analyses here, have they been adjusted for sampling effort?
The reds from the data sets here, 2000 up to 2017, no. We do use, you know, our best tool for red distribution are actual reds. We can't use carcasses for that, but and that's a point for this year where we stopped sampling for reds. Escapement estimates will be used with carcass mark recapture in reaches 1 and 2. You know, since red superimposition occurs up there, mark recapture provides a better estimate of escapement on those areas. And then downstream where there's significantly less superimposition and reds are more sparse, I think the red counts are a better estimate of escapement. So it's kind of a best tool for the job, above and below reach 2. Did that answer the question?
Does anyone else have any other questions?
There is no change to, or no adjustment for sampling effort, but probably for the 2002 to 2017 data, that I'm presuming that's not really needed. Sampling effort's been fairly uniform and.
Oh yeah. These are complete seasons of sampling. It was only in 2021 where we ceased red counts. Once, and I think it was like mid-November when reds just became indistinguishable. You know, that fresh gravel was uniformly colored. There was just very low confidence in the crews to be able to distinguish reds. And I don't know, I think Chris has seen it firsthand. I haven't, but yeah, it sounded like one just giant red field of spawning activity.
All right, anyone else with any questions for Steve? Oh, I just see a hand went up. Kyle?
Yeah, I guess you know, I've been tracking the weekly updates and seeing that the number of reds is basically around average. So are none of those reds after that point that were constructed in Reach 1 included? And does that mean once the carcass information has been processed, we would expect that would rise significantly?
Maybe. I mean, you know, like we don't know what how carcasses are going to be expanded, following the mark recapture calculation. But in those weekly update graphs, I did change that to just be limited to reaches 2 through 7.
Oh, so the what it's being compared to is 2 through 7 as well.
It's compared to the same spatial data set.
Okay, yeah, that helps.
I started excluding reach 1 from all years, and then reaches 9 and 10. Previously, that graph was reaches 1 through 10, and we also omitted 9 and 10 because we couldn't access those reaches this year because of road construction and fire and all the complications that came with that. So yeah, the more recent updates are comparing reaches 2 through 7 to previous years of reaches 2 through 7.
I'm not seeing any more hands, so I guess we'll just conclude this session. And we will hopefully be doing a in-person thing in the spring. So keep a lookout in your emails for that once we get that figured out. But thanks everyone, and thanks to all the presenters who presented for this, and hope to see everyone soon.
Thanks, Chris.
Thank you.
Thanks, everybody.
Thanks.
Yeah, thanks everyone.